Good morning, everyone. My name is Aninda Sharma Onik, and I am honored to present my research project titled AI Driven Flood Prediction and Survival System, a dual branch neural network approach with REG integration. The motivation behind this project is clear. Floods are among the most destructive real time, uh, most destructive and unpredictable natural disasters on Earth. My project aims to harness the power of artificial intelligence not just to forecast floods with exceptional accuracy but to provide real time region specific survival guidance using the retrieval augmented generation or REG. In short, it's about turning predictions into action. Floods cause billions in losses each year and displace millions of people globally. Due to climate change, both the frequency and intensity of these events are increasing. Conventional hydrological or statistical models, although scientifically grounded, often struggle with incomplete data, nonlinear relationships, and rapidly changing weather conditions. AI provides a way forward by analyzing massive multi source datasets, hydrological and temporal. AI can uncover complex, nonlinear correlations that human defined equations often miss. In this work, AI achieved a six-fold improvement in flood predictions accuracy and reduced forecasting time from roughly 24 hours to matter of minutes. This efficiency opens the door to truly proactive disaster management rather than reactive response. Traditional models such as physically based hydrological simulations or regression based statistical approaches require high precise spatial data and often fail when conditions deviate from historical norms. In contrast, machine learning and deep learning models excel at generalizing from complex patterns. Techniques like support vector machines, random forests, and recurrent architectures like LSTMs have all contributed to flood prediction research in recent days. Especially hybrid architectures that combines multiple learning paradigms show the greatest promise. You can see this system builds upon this insight through a dual branch neural network, integrating a dense hierarchical learning path with a residual stability path. This design enables both deep pattern recognition and smooth gradient flow, yielding accuracy and reliability beyond what single branch networks or classical models could achieve. This dataset I used here is combined of two countries, Bangladesh and India, the flood detection data representing uh, diverse topographies, climates, and hydrological conditions. It overall includes over 15,000 records and 9 features such as temperature, humidity, precipitation, wind speed, air pressure, and river water level. Especially these, we engineered meaningful temporal and environmental indicators like month, season, and monsoon status, and weather indices such as the heat index, precipitation intensity, and low pressure indicators. Dual branch architecture for enhanced feature extraction stability. Now let's explore the heart of this model of for any model. In this case it is the dual branch network neural architecture. The first branch is a dense branch responsible for hierarchical feature extraction. It passes through several linear layers with ReLU activation, batch normalization, and dropout, progressively distilling meaningful representations. The second is a residual branch which facilitates a gradient flow and prevents vanishing gradients, one of the biggest issues in deep networks. It maintains this information stability through skip connections. After independent learning, the outputs of both branches, 64 and 128 dimensions, overall 192 dimensions respectively, are concatenated and passed through a final classification head that predicts flood probability. This lightweight network has about 95,000 trainable parameters implemented in popular PyTorch module and trained using binary cross entropy loss. Their design achieved a strong balance between performance and interpretability and computational efficiency. Now into the agent. One of the most innovative components of this system is the retrieval augmented generation agent, which is RAG. While many AI models stop at making predictions, in this case I did a RAG integrations, converting model outputs into human readable context aware survival guidance. Basically, once the flood prediction model outputs a risk probability, if that probability exceeds a certain threshold, this RAG agent is triggered. It retrieves relevant information from a knowledge base. It could be a web browser or PDF containing official safety protocols, disaster manuals, and humanitarian guidelines, then generates a concise survival report. This means the system doesn't just alert people that flooding may occur, it tells them what to do next, how to prepare, where to go, and what resources to gather. This human-centric layer transforms a technical model into a life-saving assistant. This RAG framework has two synergistic components, a retriever and a generator. The retriever uses FAIS, that means FAISS vector search, combined with sentence BERT embeddings, embedding technique it is, to locate the most relevant pieces of information from the knowledge base that I have given. The generator is a fine-tuned T5 transformer that performs conditional text generation, producing natural, concise, and contextually appropriate survival guidance. As I said before, the knowledge base draws from sources like Red Cross disaster manuals, humanitarian protocols, and national emergency guidelines. This could be text files or PDF files inputted there in the model. The output is formatted for accessibility, including immediate evacuation actions, shelter locations, emergency contact numbers, and required supplies, optimized for mobile devices too, and dashboards. So this is it in this case. To ensure unbiased learning, I adapted a stratified split, maintains proportion of flood, no flood, the distributions correctly, allocating you can see 70% of data for training, 15% for validation, and finally the other 15% for testing, while preserving the natural distribution of flood and non-flood cases. During training, I incorporated early stopping, which holds training when validation loss plateaus to avoid overfitting. I also used reduce aileron plateau, dynamically lowering the learning rate for final optimization, and model checkpointing to save the best performing model. Together, these techniques form an intelligent training workflow that ensured stability, efficiency, and generalization. Now to the results. As you can see, finally, overall this table in the final results, this model achieved 99.96 accuracy on training data, 99.2% on validation, and impressive 99.8% on test data. Precision, recall, and F1 score all hovered around 0.99 with an ROC of 0.999, indicating almost perfect separation between flood and non-flood cases. These small performance gaps between training and validation demonstrated excellent generalization, a rare achievement in this kind of modeling. Overall, these results suggest that the dual branch network not only feeds the data well, but captured real causal relationships rather than memorizing patterns. Now the visualizations. The visualizations confirm strong classification and reliable probabilities. This visual analysis provides additional confidence. As you can see in the confusion matrix, it shows high true positives and true negatives with almost negligible false outcomes, confirming reliable classification. On the other hand, as you can see, the ROC curve with an area under the curve of 0.999 illustrates near perfect discrimination ability at varying thresholds. This visualization showed that the model's probability outputs are well calibrated, meaning it doesn't just predict correctly, it predicts with trustworthy confidence. This level of reliability was crucial when the results guide real-world disaster response decisions. Precipitation and water levels as influential factors. Feature importance analysis provided valuable insights. Precipitation intensity emerged as the most influential factor, followed closely by total participation at millimeter size, and then the river water level, and lastly the heat index and temporal features. Contextual features like this heat index and temporal patterns, including seasonal or monsoon indicators, significantly enhance model interpretability. From a policy perspective, these findings reaffirm that continuous monitoring of rainfall and river levels is essential for flood preparedness. It also means that this model can help identify high-risk regions, enabling governments to allocate resources and issue warnings proactively. To conclude, this research demonstrated a complete pipeline, from AI-driven predictions to automated survival guidance. The dual branch network delivered near perfect predictive accuracy, and the RAG agent ensures that the predictions translate into clear and practical instruction. Looking ahead, I plan to integrate real-time IoT sensors and satellite imagery for continuous monitoring, explore multiple data fusion, and include explainable AI techniques to make this system more transparent and even more trustworthy. In essence, this project isn't just about technology, it's about empowering people with timely information that can save lives. Overall, this was my project. Thank you all for your time and attention. Thanks all.